The Kuiper Belt represents one of astronomy's most significant discoveries of the late 20th century, fundamentally transforming our understanding of the solar system. This vast region beyond Neptune harbors millions of icy bodies that preserve crucial information about our planetary system's formation and evolution. The story of its discovery spans decades, combining theoretical predictions, technological advancement, and observational perseverance, ultimately revealing that our solar system extends far beyond what was previously imagined. The story of the Kuiper Belt begins long before its actual discovery, rooted in theoretical work dating back to the early 20th century. In 1930, Clyde Tombaugh discovered Pluto, which would later be recognized as the first known Kuiper Belt object, though at the time it was classified as the ninth planet. Pluto's discovery marked the beginning of humanity's exploration of the outer solar system frontier, but it would take many more decades before scientists realized that Pluto was merely one member of a vast population of objects. The theoretical foundations for the Kuiper Belt were laid in the 1940s and 1950s. In 1943, Irish astronomer Kenneth Edgeworth published papers suggesting that the outer region of the solar system might contain numerous small bodies. He proposed that beyond Neptune, the primordial material of the solar system would have been too widely dispersed to form planets, instead condensing into a multitude of smaller objects. This was a remarkably prescient insight, considering the limited observational data available at that time. In 1951, Dutch-American astronomer Gerard Kuiper published a scientific paper that speculated about objects beyond Pluto. Interestingly, despite having the belt named after him, Kuiper's hypothesis differed significantly from our current understanding. Kuiper actually believed that such a belt no longer existed, suggesting that Pluto's gravity had scattered these objects to the more distant Oort cloud. This ironic twist highlights how scientific discovery often progresses through various iterations of theories, some aspects proving correct while others require revision. The region is sometimes called the Edgeworth-Kuiper Belt to acknowledge both astronomers' contributions, though the shorter name Kuiper Belt has become more common in scientific literature and public discourse. Both scientists deserve recognition for their forward-thinking hypotheses about the outer solar system's structure, even if their specific predictions did not entirely match what would eventually be discovered. Despite these early theoretical predictions, confirming the existence of objects beyond Pluto presented enormous observational challenges. Kuiper Belt objects are extremely distant, very small relative to planets, and have dark surfaces that reflect little sunlight, making them incredibly faint when viewed from Earth. In the mid-20th century, astronomical technology simply wasn't advanced enough to detect such objects. After Pluto's discovery in 1930, it would take an astonishing 62 years before astronomers confirmed the second Kuiper Belt object. This long gap wasn't due to lack of interest, but rather to the formidable technical hurdles involved. Pluto itself was only detectable because it has a relatively bright reflective surface compared to many other Kuiper Belt objects, and is among the largest bodies in that region. Most other Kuiper Belt objects are much smaller and darker, requiring far more sensitive detection methods. By the 1980s, astronomical technology had advanced significantly. The development of charge-coupled devices, CCDs, revolutionized astronomy by providing electronic light detectors far more sensitive than traditional photographic plates. Larger telescopes with improved optics further enhanced astronomers' ability to detect faint objects. These technological improvements, combined with sophisticated computational techniques for image analysis, finally gave astronomers the tools needed to search effectively for objects beyond Pluto. As technology improved, additional theoretical work in the 1980s reinforced the case for a population of objects beyond Neptune. In 1980, Julio Fernandez suggested that a belt of objects beyond Neptune could be the source of short-period comets observed in the inner solar system. This hypothesis was further developed by Martin Duncan and others in 1988, providing a mathematical framework for how such objects might evolve into comets. These theories addressed a long-standing astronomical puzzle: the origin of comets with orbital periods of less than 200 years. While long-period comets could be explained as originating from the distant Oort cloud, short-period comets required a different source region. A belt of objects beyond Neptune offered a compelling explanation, as gravitational interactions with the giant planets could occasionally send these objects into the inner solar system, where they would become visible as comets. This theoretical work provided additional motivation for astronomers to search for objects beyond Pluto, as finding such objects would not only expand our knowledge of the solar system's structure, but also potentially solve the mystery of cometary origins. The confluence of improved technology and strengthened theoretical justification set the stage for a focused observational effort in the early 1990s. The definitive discovery of the Kuiper Belt came on August 30th, 1992, when astronomers David Jewett of the University of Hawaii and Jane Liu of the University of California, Berkeley, identified a faint object moving beyond Neptune's orbit. This object, designated 1992 QB1 in accordance with astronomical naming conventions, represented the culmination of a systematic search that the two astronomers had conducted over several years. Jewett and Liu had been using the 2.2-meter telescope at the University of Hawaii's Mauna Kea Observatory to methodically scan regions of the sky where trans-Neptunian objects might be found. The discovery of 1992 QB1 required not only advanced equipment, but also considerable patience and observational skill. Such distant objects move very slowly against the background stars, requiring observations over multiple nights to confirm their motion and distinguish them from more distant background objects like galaxies. The discovery was reported in the scientific journal Nature in April 1993, with Jewett and Liu suggesting that 1992 QB1 might represent the first detection of a member of the Kuiper Belt. They explicitly connected their observational finding to the earlier theoretical work by Edgeworth-Kuiper and others, recognizing that they had found the first concrete evidence for a population of objects that had been hypothesized decades earlier. 1992. QB1 is a relatively small object, estimated to be roughly 150 miles, 240 kilometers in diameter. Unlike Pluto, which is large enough for its gravity to pull it into a spherical shape, 1992 QB1 is likely irregularly shaped. Its discovery marked a watershed moment in solar system astronomy, confirming that Pluto was not a solitary outlier, but rather part of a much larger population of objects beyond Neptune. Following the discovery of 1992 QB1, confirmation of the Kuiper Belt's existence came quickly as astronomers around the world joined the search for additional trans-Neptunian objects. Within months, a second object designated 1993 FW was found, and by the end of the decade, dozens of Kuiper Belt objects had been identified. These rapid discoveries confirmed that 1992 QB1 was not an anomaly, but rather the first detected member of a vast population of bodies. As observational surveys continued and became more sophisticated, the rate of discovery accelerated dramatically. Today, thousands of Kuiper Belt objects have been catalogued, though this likely represents only a tiny fraction of the total population. Estimates suggest that the Kuiper Belt may contain millions of objects larger than 1 kilometer in diameter, with the vast majority still too small or distant to be detected with current technology. These discoveries revealed not only the abundance of Kuiper Belt objects, but also their diversity. They vary considerably in size, orbital characteristics, surface properties, and likely composition. Some follow nearly circular paths close to the plane of the solar system, while others have highly elliptical or inclined orbits. This diversity has provided crucial insights into the complex dynamical history of the outer solar system and the processes that have shaped it over billions of years. As more objects were discovered and their orbits determined with precision, a clearer picture of the Kuiper Belt's structure emerged. The region extends from approximately 30 astronomical units AU from the Sun, the orbit of Neptune, to about 55 AU, forming a disc-shaped region roughly 25 AU in width. This vast area contains a diverse array of objects organized into several distinct dynamical populations. The classical Kuiper Belt consists of objects in relatively stable, nearly circular orbits that have not been significantly perturbed by Neptune's gravity. These objects, sometimes called Kubewanos after 1992 QB1, primarily orbit between about 42 and 48 AU from the Sun. They generally have low orbital inclinations, forming a relatively flat disk that likely represents the most pristine population of Kuiper Belt objects, preserving information about the solar system's original protoplanetary disk. In contrast, the scattered disk population exhibits more eccentric and inclined orbits, with some objects traveling more than 100 AU from the Sun at the farthest points in their orbits. These objects are thought to have been scattered into their current orbits through gravitational interactions with Neptune early in the solar system's history. The scattered disk effectively extends the reach of the Kuiper Belt to much greater distances and provides a transitional population between the classical Kuiper Belt and the even more distant Oort cloud. A third significant population within the Kuiper Belt consists of objects in orbital resonances with Neptune. These resonant objects orbit the Sun in periods that maintain a simple integer ratio with Neptune's orbital period. Pluto, for example, orbits in a 3.2 resonance, completing 2 orbits for every 3 of Neptune's. These resonant relationships provide stability to orbits that might otherwise be destabilized by Neptune's gravitational influence, allowing objects to persist in regions where non-resonant objects would be ejected over time. Kuiper Belt objects are predominantly composed of frozen volatiles such as methane, ammonia, and water ice, mixed with various organic compounds and silicate materials. This composition reflects the low-temperature environment in which these objects formed and have existed for billions of years, far from the Sun's heat. The specific mixture of materials varies between different Kuiper Belt objects, providing clues about the conditions in different regions of the early solar nebula. Despite the enormous spatial extent of the Kuiper Belt, the total mass of all objects within it equals only about 10% of Earth's mass. This relatively low mass suggests that the current Kuiper Belt is merely a remnant of a much more massive primordial disk. Theoretical models indicate that the early solar system may have contained 100 times more material beyond Neptune, with most of this material subsequently ejected through gravitational interactions with the giant planets during the solar system's chaotic early history. The surface compositions of Kuiper Belt objects can be studied through spectroscopic observations, which analyze the wavelengths of light reflected from their surfaces. These studies have revealed a diversity of surface characteristics. Some objects, like Pluto, have highly reflective surfaces due to fresh frost deposits, while others appear much darker, possibly due to the long-term effects of cosmic radiation on surface ices, producing complex organic compounds. These variations in surface properties help astronomers understand the dynamic processes affecting these distant worlds. While thousands of Kuiper Belt objects have been discovered, several stand out due to their size, composition, or historical significance. Pluto, long considered the 9th planet, is now recognized as one of the largest members of the Kuiper Belt. Other significant objects include Eris, discovered in 2005, which is slightly smaller than Pluto but more massive, suggesting a higher density and different internal composition. Additional large objects include Haumea, notable for its elongated shape resulting from a rapid rotation, and Makemake, which, like Pluto and Eris, has enough mass for its gravity to pull it into a nearly spherical shape. The discovery of Eris, initially thought to be larger than Pluto, prompted a fundamental reconsideration of how we classify objects in our solar system. This reevaluation culminated in the International Astronomical Union's 2006 decision to create a new category called dwarf planets for objects that orbit the Sun, have sufficient mass to assume a nearly round shape due to their own gravity, but have not cleared their orbital neighborhood of other material. Under this definition, Pluto was reclassified as a dwarf planet rather than a planet, a decision that reflects the scientific reality revealed by the discovery of the Kuiper Belt, that Pluto is more appropriately grouped with its Trans-Neptunian neighbors than with the 8 larger planets. While this reclassification sparked public controversy and emotional responses, from a scientific perspective, it represented a more accurate categorization based on our enhanced understanding of the solar system's structure. Rather than diminishing Pluto's importance, the recognition of its status as a Kuiper Belt object actually elevated its scientific significance as the first discovered and one of the largest members of this important population of objects. Most of what we know about the Kuiper Belt comes from observations using ground-based telescopes and the Hubble Space Telescope, but these remote studies are limited by the vast distances involved. Even the largest Kuiper Belt objects appear as mere points of light through Earth-based telescopes, revealing little about their surface features or detailed compositions. To truly understand these distant worlds required direct exploration by spacecraft. NASA's New Horizons mission provided this crucial close-up examination. Launched in January 2006, the spacecraft traveled for more than 9 years before making its historic flyby of Pluto on July 14, 2015. This encounter transformed our understanding of Pluto, revealing a complex and geologically active world with mountains of water ice, vast plains of frozen nitrogen, and evidence of recent geological activity. These discoveries challenged the prevailing view of Pluto as a simple, inert ball of ice and demonstrated the remarkable diversity of environments in the outer solar system. Following its Pluto encounter, New Horizons continued deeper into the Kuiper Belt, adjusting its trajectory to visit a smaller Kuiper Belt object initially designated 2014 MU69 and later named Arrokoth. This second encounter, occurring on January 1, 2019, was the most distant planetary flyby in history, taking place more than 1 billion miles beyond Pluto. The flyby revealed Arrokoth's unusual bilobate snowman shape, formed by the gentle merger of two smaller bodies, providing valuable insights into the processes of planetesimal formation in the early solar system. The New Horizons mission represents the only direct exploration of the Kuiper Belt to date, and its findings have revolutionized our understanding of this region. The spacecraft continues to operate in the Kuiper Belt, collecting data on the space environment in this distant region and conducting distant observations of other Kuiper Belt objects. These ongoing operations extend our presence in the outer solar system and continue to provide valuable scientific data from a region that remains largely unexplored. The discovery and ongoing study of the Kuiper Belt have profound implications for our understanding of the solar system's formation and evolution. Kuiper Belt objects are believed to be remnants from the early solar nebula, preserving a record of the materials and conditions that prevailed when our planetary system was forming more than 4.5 billion years ago. Unlike the planets, which have undergone significant geological processing, most Kuiper Belt objects have remained relatively pristine, offering a window into the past that is unavailable elsewhere in the solar system. The Kuiper Belt also plays a crucial role in our understanding of comets and their relationship to Earth. Many short-period comets are believed to originate from the Kuiper Belt, sent into the inner solar system through gravitational perturbations. These comets may have delivered essential ingredients for life to the early Earth, including water and organic compounds. By studying the Kuiper Belt and its objects, astronomers gain insights into the potential contributions of comets to Earth's habitability and the development of life on our planet. The discovery of the Kuiper Belt necessitated significant revisions to models of solar system formation and evolution. Current theories suggest that the Kuiper Belt we observe today is just a small fraction of a much more massive disk that originally extended beyond Neptune. Gravitational interactions with the giant planets, particularly during a period of orbital instability early in the solar system's history, ejected most of this material, leaving behind the relatively sparse population we see today. These same interactions shaped the complex orbital structure of the Kuiper Belt, creating the distinct dynamical classes we now observe. The discovery of the Kuiper Belt has implications that extend beyond our own solar system. Observations of debris disks around young stars suggest that Kuiper Belt-like structures may be common features of planetary systems, representing a normal stage in their evolution. The study of our own Kuiper Belt provides a template for understanding these distant systems and developing more comprehensive models of how planetary systems form and evolve throughout the galaxy. Astronomical observations have identified several stars surrounded by disks of dust and debris at distances comparable to our Kuiper Belt. These structures, often called debris disks, are thought to be composed of planetesimals and the dust generated by their collisions, analogous to the processes occurring in our own Kuiper Belt. Some particularly well-studied examples include the disks around the stars, Fomalhaut, Beta Pictoris, and Epsilon Eridani. These observations suggest that the presence of a belt of small bodies in the outer regions of a planetary system may be a common outcome of the planet formation process. If so, The discovery and characterization of our Kuiper Belt may provide insights that are applicable to planetary systems throughout the galaxy, helping astronomers develop a more universal understanding of how planets form and evolve. The study of the Kuiper Belt remains an active and evolving field, with numerous directions for future research. Ongoing observational surveys continue to discover new Kuiper Belt objects, gradually building a more complete census of this population. As more objects are identified and their orbits precisely determined, astronomers gain a better statistical understanding of the Kuiper Belt's structure and dynamics, refining models of its formation and evolution. Advances in observational technology promise to enhance our ability to study Kuiper Belt objects remotely. Next-generation telescopes like the James Webb Space Telescope will provide unprecedented sensitivity and resolution, enabling more detailed studies of the sizes, shapes, and surface compositions of numerous Kuiper Belt objects. These observations will reveal patterns and relationships that are currently obscured by the limitations of existing instruments, potentially leading to new insights about the processes that have shaped the outer solar system. Future spacecraft missions could provide additional close-up examinations of Kuiper Belt objects, building on the success of New Horizons. While no such missions are currently in development, various concepts have been proposed for missions that would orbit or land on Pluto or other large Kuiper Belt objects. Such missions face significant challenges related to the vast distances involved, but advances in propulsion technology and mission design may eventually make them feasible, opening a new chapter in our exploration of these distant worlds. The discovery of the Kuiper Belt represents one of the most significant expansions of our understanding of the solar system in the modern era. From theoretical predictions in the mid-20th century to the definitive discovery of the first Kuiper Belt object in 1992 and subsequent exploration by the New Horizons spacecraft, our knowledge of this distant region has grown tremendously. What was once thought to be an empty void beyond Neptune has been revealed as a complex and populated region housing millions of primordial objects that provide crucial insights into our solar system's history. The story of the Kuiper Belt's discovery exemplifies the scientific process at its best. Theoretical predictions based on limited data, technological advancements enabling new observations, and the patient, systematic work of dedicated researchers resulting in breakthrough discoveries. This process continues today as astronomers work to fully characterize the Kuiper Belt and understand its role in the formation and evolution of our solar system. As our exploration of the Kuiper Belt continues, it remains a frontier of solar system research, full of potential discoveries and insights. Each new observation and spacecraft mission brings us closer to understanding this distant region and its significance for our cosmic origins. The Kuiper Belt reminds us that even after centuries of astronomical research, our solar system still contains regions largely unexplored and mysteries waiting to be solved, inspiring continued curiosity about our place in the universe.